Okay. All right. Well, a little bit behind here, so I'm going to try and speed through these slides. Hopefully I'll get to them all. Thank you all for coming. My name is Matt Hansen. I'm with Element 84. Today I'm going to be talking about AI, everybody's favorite topic. It's the hot topic of the day. I really have to give a special thanks to my colleague Jason Gilman at E84. He's our AI ML lead, and he's responsible for a lot of the content on these slides. Okay, so AI for geospatial. So first, every geospatial project begins with a quest for answers, right? So users have questions such as, what are the current cases of Lyme disease? How much deforestation is happening within a certain area? These are ultimately, this is what we're after when, as GIS analysts, these are the answers that these are the questions that we're trying to answer. And we have those answers in data. That data is in documentation and data in the cloud and metadata. We might have databases, APIs. These are all things that would be used in order to answer these questions. So how can we apply AI ML to answer these questions? Well, first, I want to say, what can a user ask now? So we've seen the rise of large language models, and what can a user ask right now? If you go to ChatGPT and ask these questions, you'll actually get some pretty decent answers, right? Like you can say, what data sets are available for sea surface temperature? And you'll get some clues, and you'll get some direction on, like, yeah, maybe you should be looking at this, and you can access this. How can I access MODIS data? It might not be entirely correct, but you can get a lot of the way right now with this. But this is a far cry from the previous questions that we had. So we can envision a geospatial computer here, right? We've got users, we've got all sorts of users. We've got policymakers, scientists, general users, and we have all the data over here. So we can imagine there's some sort of interface here, right? So we'll call it a geospatial computer. What's it look like? What are the components inside? Well, there's conversations with the user. We have some sort of AI. We have a broker that's interfacing with the user and asking questions and collecting data. And here we have a vector database that is a vector representation of all of this data. And we use knowledge graphs so that the AI can understand how to navigate the data in order to answer these questions. So I know this is really high level. But I mentioned this vector database, and this is key. So here's all our data, and I'll talk more about vector embeddings later, but here's our vector database, and this is a key part, is we need to index all of this data in a vector representation and store that in a vector database. And this is called RAG. This is called Retrieval Augmented Generation. And what it is rather than relying just the LLM to give responses, we have the LLM retrieve actual data from a database and return that. So I'm going to give some practical examples, and I'm not going to give demos, but I do have demos that if you come up later, I could show you some examples of it working in real time. So geocoding. Okay, here are the questions that I showed you before, right? I underlined the spatial component here. So what are the current cases of Lyme disease within 20 miles of Boston? What are the major drought-affected areas in southern Madagascar? The first thing that an LLM needs to do, this interface needs to do, is pull out that geospatial information and figure out where it is that you're talking about. What's the AOI? So in traditional geocoding, we have an address. There's lots of geocoding APIs out there. You have an address, and it's going to convert it into a lat long. So this is how geocoders on any sort of map work. And so you'd think, well, large language models, they know how to, maybe they can create GeoJSON. Anybody tried this before? Use ChatGPT to create GeoJSON? Yeah, so here, all right, generate a GeoJSON polygon that covers within 1 kilometer of the Iberian Peninsula. All right, well, if you ask ChatGPT to do that, it will create, this is some GeoJSON here. This is a feature collection, and it looks like that. All right, it thinks it's creating something. It creates something that is GeoJSON. It's valid GeoJSON, but it has no idea, has no concept of spatial locations. So the large language model by itself is not enough. So what we want is this. So within 10 kilometers of the coast of the Iberian Peninsula, and here we have a buffered location around Spain and Portugal along the coast here. So how do we do this? Well, the first thing is that we need to look up the place, right? We need to get, so here's the place look up, so the Iberian Peninsula, all right? That's the whole area. We want the coastline of just that area, and then we want the buffer of that. So we can use the large language model in order to create a tree representation of what that process looks like. So within 10 kilometers of the Iberian Peninsula, use the LLM to convert this into some sort of JSON representation. We have a named entity, all right? We have a buffer, okay? We have the coast of, and we're buffering this out 10 kilometers. So this is the real trick here, right? Is to get to that, and the LLMs are really good at that. You can tell the LLM, I want a tree representation, follow this structure, do this. This is what you're trying to do. And now we can take this tree representation, and now we can use that. We're done with the LLM at that point, where we can use that. We can look up the locations that we need, and we can do any sort of spatial calculations we want in order to create that GeoJSON. And there is a demo of this working. We originally had come up with this idea because we wanted to use natural language to discover data in a STAC catalog. And so this also we have a working demo here. So like in this case, it's show me Sentinel-2 data over the Senegal coastline with low cloud coverage. And so it's getting the coastline, and then it's actually creating the STAC. This is a STAC query. It figures out the STAC collection. It gets the date time for 2021, and now we can use that, and we can send that we can post that directly into the STAC API in order to get these scene results here. So let's look at some more complicated examples. So here we're seeing within a few miles of Salt Lake City, West Valley City, and Mill Creek, except for the airport. All right. So here we have a polygon with a hole in the middle of it. So the way that this works is that we're using Nominatum, the OpenStreetMap API. And the reason why we're doing that is because OpenStreetMap has polygons. You don't just get points. A lot of geocoding APIs will just return points, but Nominatum will return polygons. And there's a polygon of Salt Lake City. So this is the boundary of Salt Lake City. And so if we just put in Salt Lake City into our geocoder, our natural language geocoder, that's what we get. If we say Salt Lake City east of the airport, well, it's looking up the airport, and then we have an intersection calculation, and now we're getting Salt Lake City just east of the airport. If we say Salt Lake City and West Valley City, we're encompassing we just combine, we take the union of both of those polygons there. We have looked them both up in the Nominatum API. And here, you can say this is within 3 miles of Salt Lake City. This is a buffer. So we can deconstruct this. So this is really just the deconstruction of several different spatial locations, and then we create that tree representation and then just perform those fairly simple geometric operations in order to create this more complex polygon here from the text of within a few miles of Salt Lake City, West Valley City, and Mill Creek, except for the airport. So GIS folks in the audience here, I suspect that you probably see this as super useful because creating these AOIs by hand can be really time consuming. If you want to create complex boundaries based on administrative boundaries, you have to get all the data, and then you've got to select which entities you're interested in and then perform the calculations. So this is a great example. I know there's lots of hype about AI, but this is a great example of something that's really concrete and fairly simple that I think is one of the perhaps the most useful early applications that we're seeing come out of large language models. This is just showing the tree representation here. We have 3 place lookups in this case, Salt Lake City, West Valley City, and Mill Creek Airport. There is an open source repo for this. This is FOSS4G after all, so you can look on our GitHub at Element 84. There's natural language geocoding. We don't have a public demo right now. I have a demo running, but it's behind some authentication. This you could use with your own Nominatum API, but we're using it with just the publicly available API, which is why we don't want it publicly available, because we don't want to hit that API too hard. But you can try and run this yourself. So challenges. There are some challenges, of course, because OpenStreetMap's not perfect. Sometimes, in this case, like this is the island being mapped twice with two different types. So these types of relational problems in OpenStreetMap can cause issues. Sometimes there's no polygons for some areas, so that can be a problem as well. So like the Florida Keys, in this case, is just a point. It's not actually a polygon, and so it's not going to work for that. Finding the right entity, the right entry, is sometimes an issue. So if we put in Mississippi River, right, well, that could be any part of the river. There's a lot of different options here. The Mississippi River is very large, and there's many tags of it in OpenStreetMap. And so you might not actually end up pulling the right entity from OSM in order to do this. Which Paris? All right. Let's say I want something in Paris. Well, there's Paris, but there's actually more Parises in the U.S. than there is in France. So what can we do about this? Well, we can curate our areas, right? We can create our own Nominatum API. Maybe we can put in some watershed boundaries. We could put in sources. We could put in some government sources or our own data, and actually curate it so that the areas that are within our geocoding API are the areas that we are most interested in. Of course, this is most useful for more specific applications and not general applications, but this would be one option. You can also provide context based on what the rest of the query is, right? Like if I want some ice cream stores between Austin and Paris, but maybe if they said très bien, then you could infer that maybe that's actually France. So that's another thing, is the LLM could potentially infer that, and LLMs are good at that sort of thing. But more likely, I think that as we go on, this will be a negotiation. This will be ask the user type of situation. Like the LLM, they're really good at doing interaction, right? And so if the LLM doesn't quite have enough information, it should ask. So, hey, do you mean Paris, France? No, I don't mean that one. So this is a great way to do it, and this can really provide a lot. You just have the user provide the clarification here. Okay, so that's geocoding. The second thing I want to talk about is vector embeddings. I mentioned this at the beginning. So what are vector embeddings? Well, there's some sort of model, and you have some sort of text, like this is for vector encoding words. And we have some sort of model that takes that text and puts it in some sort of vector representation. Now, we can do the same thing with images now, because there's a whole lot of open source models. They're called clip models. We have been using one called SkyClip. There's a few others. And more generally, they're called vision embedding models. And these are models that will take an image and create a vector representation of that. So now with text embedding, okay, we're really talking about capturing, the vector embeddings are capturing the semantic meaning of that text, which is why LLMs are good at translation, for instance, or for understanding that two phrases are actually semantically similar, even though they might be using different words. So we could, in a really simple plot here, we can see that if we throw a bunch of words, that was the last one. If we throw a bunch of words on a plot, it's the absolute location of these is not important, okay, but the relative location of them. So potatoes and carrots are similar because they're tubers, right? And a window might be here in the middle, and defenestration is down here, which is throwing a person out a window, and like it's somewhat close to the window, but like where does this go? So like it's a complicated space that is actually hundreds or thousands of dimensions, right, in this space. And the closer things are, that relative distance is what indicates how similar things are to one another. So we can do this with imagery. So the distance of a vector embedding from a target image shows how similar they are. So here's like a reference image. It's showing some forest. And we see that these are also forests, and so they're fairly close. But as we get some more clear-cut areas, we actually are getting further away. This is an urban area, and so it's much further away in this vector space. So if we take all our data, we put it in our vector database, all right, we can do cool things like this, right? So we've done this. We have a demo for this, and there's an open source repo. And we've done this for Massachusetts, the state of Massachusetts in the U.S., where we took the NAIP data. This is publicly available high-resolution data. And we created the vector embeddings using SkyClip for the entire state for 1 year. And now you can do things like, I want a house with a swimming pool. It's taking that text, it's creating a vector representation of that, and combining it with the labels that were used in the vision embedding model in order to get images that are semantically similar to the text here. So we can search for houses with swimming pools, for instance, or a large solar farm, or really anything that you can think of. So now, if we combine that with the geospatial coding, we can do some really interesting things, like show me algae within 2 kilometers of the coast of Cape Cod. So here we've created our coastline of Cape Cod, and we are finding all of the image chips here with algae in them. Show me new construction within this certain area. So as you can see here, these images are all showing some level of construction within that area. And water facilities here, water treatment facilities, and liquid gas storage. So there's a lot of different examples there of different things. This is an open source repository that you can do. You'd have to create the vector embeddings here yourself, but you can learn more at this repository. A few other notes here on other potential uses in case, if you think about like what could we possibly do with this? Land cover, right? Like in this case, we have created a land cover map just by searching for forested areas, urban or built-up areas, and water bodies, and then just mapping those. So without having to do any specialized training, we can now create a land cover map for whatever types of land cover map for whatever kind of cover types it is that we want. So in this case, we've created a land cover map without any additional training. This naturally comes out of the vision language model. This also has some implications for doing change detection. So if you have all of these vector representations in a vector database, then you could use a SQL statement in order to do change detection, in order to calculate large areas of change between multiple years, for instance. So in this case, we see between 2018 and 2021 that some of this forest has been turned into a quarry. And in this case, we're finding forests that have been cleared for houses within 5 miles of this reservoir, and it's comparing data from between over a 3-year period, I think in this case, and here we've targeted these locations on the map of where we've seen that type of change. There's a blog post from earlier this year that we put up that you can check out that explains how this vision language model can be used in this case. So this I think will give you the basics if you want to learn more. And you can read about it there. And that's all I got today. Thank you.